All right. All right. Okay, so first off, before we start stuff, I'm going to switch over the monitor here. I don't know if everybody has. Sorry. Has seen the. Oh, nuts! Cursives. I can't, for some reason I don't seem to be able to see. All right, guys up in Vancouver, I'm going to briefly, and guys on YouTube, I'm going to briefly go to the, on YouTube. I'm going to go to YouTube, and we're going to look at the movie that came along with this paper, just to show you what kind of results we can expect from this, because I know some people haven't seen the movie with this. If you guys want to log into your computer or RGR into whatever the hell this machine is called, you can do it too. It's called eclipse.d2.com, but or you can just listen to me. We won't spend much time with this movie because it's just showing examples. So there you go. There's for YouTube people, you can kind of see what's going on. But you can see the results. So the whole setup here is that somebody is wearing a helmet on their head, and they've got a camera pointed right at their face. They're moving around, they're doing expressions and stuff. And in frickin' real time, you're getting the results on the right, which is a 3D representation of their face. Looks pretty good. It looks pretty solid. So only one camera is being used. The helmet actually looks kind of scary. It's got a whole bunch of stuff, but there's some lights on that helmet and things. We'll talk about lights in a bit. And then the key thing with this is, well, the key thing is, how the hell do they do it? And this little video where you're seeing expressions, camera viewpoint, and illumination changes is a really, really key part of this. So once you have this and you've trained some really cool machine learning stuff, you can, because it's machine learning, really fast compute not only what the model of the face is doing, but the pose it's got in front of the camera and the illumination changes on the face, which is pretty darn hot, right? I mean, you think about it, and not only are we, this is one of the first papers where they're actually figuring out the illumination changes. Well, they're kind of figuring out the illumination changes. We're going to get into that. What they're trying to do is make it robust to illumination changes, but they are inches away from actually computing how the illumination varies across a person's face. They don't quite make it. In fact, they comment on how it's still a little twitchy. But that would be super hot, right? I mean, if you could not only figure out the expression of a person's face, the pose of the person's face, you know, how it's oriented within the camera, but also what the light is doing on the person's face, we could use that. We could totally use that in what we do. So the results are pretty hot. They're very good, very stable, very robust. You notice that they aren't, they're comparing it with some previous work. The work on the right, the Beeler 2011, has more details. But that's an offline thing. This is all happening in real time. So, and notice the mouth shape, everything. This is all very good. So the question is, how did they do that? So we're going to stop talking about that. And we're going to go back over to the screen, and I'm going to switch views here. So it's just me. I'm going to zoom out here. So there actually see the board. There we go. How about that? There, that's so bad. All right. So this is machine learning all over the place. We'll come sliding by here if you want. What do they do? Well, first of all, they start out with number one, build a fancy, and I'm going to put the word fancy on it because it is actually fancy, blend shape model. And especially in visual effects, this is not that big of an ask. If they wanted to release this to the world, this would be a huge ask. This is something that a grandmother or something. For people who are joining on life size, make sure you're muted yourself. We can hear you. Build a fancy blend shape model that represents the character. And this is actor specific. So actor, I'll write that down because it's going to specific. So what we're going to get is a blend shape model of our actor. And remember how that stuff works. There is a base shape, B0, plus a sum of a whole bunch of, we'll call this BI, I equals 1 to n, however many blend shapes you have. And this is a weighting value. And then there's a blend shape, well, actually, let's write this out correctly. It's BI minus B0. Right, so basically, remember, going back to blend shapes, you model the shape of the face in an expression. So eyebrow up, right eyebrow up, left eyebrow up, a nose twitch, smile, all that kind of stuff. And each one of those expressions basically represents what the face can do. And the assumption is that you can get a fairly good animation of the face by simply just linearly combining those blend shapes. So what we're going to do is subtract each blend shape from the base shape, and that's going to produce a whole bunch of vectors that move the model into that blend shape. And if we wanted to make complicated expressions, you just weight multiple model or shapes highly, and some you'll turn off because they're not raising the right eyebrow, but some you'll turn on, and you can combine and make an actor-specific rig. But not only that, we also have actor-specific, so this is the rig part of it, but we also have actor-specific textures, and including subsurface scattering, subsurface stuff as well. Because what we're going to do is actually use this to train our machine learning stuff. So we can actually render this pretty. We can get good renders out of this. All right. Now, this is a bit of a thing, and this is a cool thought that these guys had. It was like, you know, renderers are getting pretty good. We can actually render a model of the face that looks pretty good. Maybe it's good enough that we can actually use it to recognize faces, you know, actually figure out where this pose is. And we'll see how this, there's the neat leap that they did is that they have some sort of machine learning that we're going to come over here and spend a lot of time thinking about. And the way it learns stuff is really simple at its core. If you give it an image, it's going to do all sorts of fancy stuff. But at its very core with this image, if it wants to figure out where your face is in that image or what your expression is doing or whatever it's doing, it's going to be doing two things. It's going to take one pixel and another pixel, kind of randomly selected, and subtract these two. So we're going to take this pixel and this pixel, so that's P0 minus P1 equals some value F. And that's it. That's all we're doing. We're comparing the brightness of one pixel with the brightness of another pixel. And that is in the image that the camera is taking. So now you're thinking, okay, if I have a decent render that responds to light correctly, and all I'm doing when I'm trying to find faces in the image is comparing differences in pixels, why can't I just render this puppy? And if it's good enough, it looks decent, that probably means that the difference in pixels of a render is actually pretty close to the difference in pixels of this, the thing that the machine learning is going to need. Now, in order for this to work, you have to have kind of a model. So not only do we have a blend shape rig, a fancy blend shape rig of our actor that looks good, but we also have sort of the knowledge of the setup. So let's put the face here. This guy is wearing a helmet, right? And on that helmet, there's a rig with a camera pointed right there. And on top of that, we've put some lights. There's a couple of lights illuminating our character. And also, this character is in a great big environment, which can be captured with a light probe. All right? So now all of a sudden, we have a way of producing what likely images that camera is going to be capturing. How do we do that? Well, we can do one thing. There's three things that we can do. We can vary the expressions. So our actor is going to be making expressions and talking. And to vary the expressions, we're just going to change the weighting on the blend shapes, right? We have a way of moving our face. Two, the camera is going to move. The camera wobbles. So this camera is actually going to move up and down and over. It's going to wander around. And in this paper, I build a model of the likely motion of the camera. So if you think that this paper is going to work, if I take the camera and move it way over here, it isn't. It doesn't know about this. It's not going to train what it's going to be learning about on that. What we're going to do is start rendering images using this camera with a built-in kind of camera wobble in it. And that wobble is going to be very constrained to what we expect the camera to do in this situation. And then three, the lighting changes, right? So these guys are like, all right, if the lighting changes, and we don't want to try to figure out every kind of lighting situation. You know, if somebody grabs a flashlight and holds it under their head, that's going to be very weird. But what we can do is put in a light probe and capture the environmental lighting of the motion capture stage, let's say, or whatever place that this guy is acting in. And also, we can characterize these lights. We know how far these lights are going to be from within the camera. So we can build a lighting model that we can relight this actor based on his head pose and the lighting that's going on. So as he moves through this environment, this light probe environment, we can re-render his face in different orientations with the appropriate lighting on it. All right? So the key thing is, if we can do this, if we can control what this thing is building and produce a bazillion images out of this, we can train this machine learning thing so that if it sees pixel differences going through this magic of machine learning, it can actually figure out the values of the blend shapes, figure out what the camera wobble is. They're a little roughly on the lighting changes. The lighting changes are a bit tricky, but we can use the lighting changes to make this thing more robust. All right. So does this make sense? Is this actually sort of, this is what we're trying to do. But there's the key thing, before we can go on to this, we have to figure out the machine learning aspect of this. And about a year ago, we talked about the paper.
Sorry, Doug, just one quick question.
Yeah, no.
So they're assuming for a pre-built full fact-based rig for this character.
Yep, and they use, this is from Disney Zurich, so they're using the Medusa system to do that, and they're set up, so they're getting high-res scans And they've got an artist sitting there sculpting the shapes and making sure the shapes work.
Got it. So it's not just all a one-stop button click, data acquisition and rig build. It's a clean, muscle-based fact shapes cleaned up from scans built into a full rig prior
Artist
to
approved. Yeah, this is
prior to fuse texture, prior to actually starting up anything.
exactly. This is not sit down in front of your camera phone. This is sit down in front of their Medusa rig, get a whole bunch of fact shapes, use those fact shapes to train a rig. Exactly. And then you can do that. But they're honest about this. They're thinking for this in like a production environment. But once you have this, we could, like if we had this, we could go out onto our motion capture stage, and then the director could actually see a preview of the actual actor's digital face, which is cool. All right, so we're gonna switch gears and totally back off. You can sort of see the goal of this, and we're gonna see where this comes from. We're gonna move now back to this paper that we covered a year ago. But a lot of you guys weren't here a year ago, and quite frankly, I'd kind of forgotten the details of this paper. So this is just a worthwhile thing to talk about again, because this paper hasn't diminished. This is a 2011 paper, and these guys are saying, you know, that 2011 paper, it works great, and we can use it in this framework. So they basically say, in one of the sections, that they are just leveraging this paper into this. You have to understand this paper in order to do that. All right, so. Hey, Australia, make sure you mute yourself. We can hear you. All right.
These are the results. Oh, this is a paper. So this is the results.
Is somebody asking a question on life size? Because I'm not able to hear. Okay, maybe we're good. Okay. All right, so this paper is called, so we're gonna sort of pause for a moment on this. And this is face alignment, and it solves a different problem too, which is interesting. You know, you can see what the current paper is trying to solve. This one is face alignment by explicit shape regression. And what they're trying to solve is much easier. So say you've got a photograph of a person, and they're smiling there, and there's trees in the background, a little building over here or whatever, and there's a person there. What we want to do is figure out not a 3D model of this guy. We want to find 68 landmarks on this guy's face, or 58 landmarks on this guy's face, or however many, I think it's around 68. And it's these red dots along there. There's some points along the jaw, there's some points on the cheek, there's various points along the mouth and eyes. And we want to find those. And we don't even care about their 3D location. What we care about is that they are nicely aligned, face alignment, to the face. So if this face turns, we want these points to turn. But all these points are 2D points. And in fact, we're going to call that out right off the bat. A shape, or S, called shape. All that is a great big vector of x, y0, y0, x1, y1, x2, y2, all the way down to x, n, y, n. And these are the red dots on this face. They are the locations of the pixel coordinates of those things on the face. All right? Yeah. The paper starts out right away. There's no leaping out of running up into this. They basically say, I want to try to figure out this. If I have a face shape, given a face image, the goal of face alignment is to estimate this shape, S, that is close as possible to the true shape. True shape. which makes sense, right? What you're trying to do is find a shape that is, you know, there's the actual points on this face that are in this thing. If you were given this image, you could probably mark out exactly where those features are. And we want to find, given our shape, we want to find a way to change the shape so it actually matches what's going on in the image. And the main problem with this is we have no idea what the true shape is. That is a great big question mark. The computer doesn't know. We have no knowledge. This is a nice equation, but we can't do anything with it because we don't know either this or that. So you hate me, don't you? All right, so how do we do this? Well, what we can do is use a technique called decision or regression forests. Or, well, this is where we're going to get into machine learning. What we're going to do, unlike in the previous or the current paper where we're rendering things, what we're going to do is take a whole bunch of pictures, on the order of thousands of pictures. And I've talked about this before, plus grad students equals a list of pictures where you have, make sure I get my notation correct here. We have a list of images, yes. We have I sub I, comma S sub I, right? And we have n of these. We have thousands of these things, where I is an image that we've downloaded from the internet of random people, because we want this to work on anything. The current paper that we're looking at works on one person. This works on, they were trying to get a facial thing that recognizes anybody. So they have image after image after image where there's a person in the image, and a grad student has created the true shape. We've actually marked out where these points are. And so you've gone and loop, 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 and we've got 68, and we press a button and go on to the next one. All right. So what we're going to do is this thing called boosted regression. Hold on. So we're going to build, so this is where the machine learning comes in, and we're going to write down a little equation here. We're going to have a shape. We're going to do this iteratively. And S is the thing that we're trying to solve, right? And we're going to say S is equal to T minus 1. And T is sort of this iterative thing. It's not time. It's you solve it once, come up with a solution, then solve it again, come up with a better solution, and solve it again, and come up with a better solution. It's basically the number of solves that you're doing here. And then plus R sub T I, comma, S sub T minus 1. All right, where T is equal to 1 to T. And T is on the order of, I think they're using about 10. Capital T is on the order of 10. So let's look at this equation and just sort of go, wait, what? So this R, this thing stands for a regressor. We'll talk about that in just a moment. But basically, think about it as a magic device that is going to take the current image that we're working on. Notice that I does not have a subscript I on this. This is just the current image that we've got from our facial capture. And we have an initial shape. And when T is 1, this would be shape sub 0. And shape sub 0 is just the neutral face in the center of the image. So we're going to take the neutral face in the center of the image and the current image that we're working on, and we're going to run through a regressor that is built to figure out what to do with a neutral shape, right? Because this guy does have an index based on the iteration that we're working on. So the first time we go through this, we're going to take our neutral shape, the image, and it's going to pop out while we're adding that to the shape, right? So this thing actually produces what they refer to as a delta S sub T shape. So this is saying, I want to take, or I'm going to add the changes that I'm going to compute here to the current shape. And when t is 1, that's going to be the base shape. And I'm going to produce the next version. And hopefully that next version is closer to the target. Now, in a web camera capture, I don't know what the target is. But I've trained this thing so well that it doesn't matter what's in the image. As long as there's a face in this image, it knows how to move things based on what it's seen over and over and over again, closer to the actual target. So this is going to discover the true shape for us without actually knowing the true shape, because all the true shape is built into the smarts of that thing. So we do this, and you can kind of think about how this would work. You know, if you were to do this, if you were to actually try to maneuver this shape onto here, the first thing you do is you kind of scale it, right? Or at least this is how I do it. You take the shape, and I'd use my scalar function. I'd scale it, I'd rotate it, I'd push it in to get it to fit. And then I'd start going a little bit more detail. And in fact, because I'm a little lazy, I would select some points, and I'd move the points so that the shape fits the face, right? And then I'd start working on individual points where I'd move an individual point a little bit and move an individual point a little bit until it just right up. But I try to do global stuff initially, and then as I get closer and closer and closer, I'm actually going to get in there and fine-tune the details of these points. That's exactly what this thing is going to do. Each time we go through this thing, it's going to start snapping this thing, and the very first step is going to find a snap that finds the face in the image. The next shape is going to, time it's going to do it, it's probably going to just sort of adjust the shape, not globally on the image, but more just to fit the face, and so on and so on and so on. And it does it 10 times. So it's going to have these 10-time iterations. The cool thing, and the reason that this is real time, is that once you compute this, once we figured out what this little R does, it runs super, super fast. Because all it's going to be doing underneath the hood is subtracting pixels. And you can do the subtraction of the pixels in parallel. You can do all these in parallel subtraction of pixels, take the results, and then move on to the next phase, and take the results and move on to the next phase. So we can find this face in this image in milliseconds. Now the question is, how do we do that? All right, so far so good? Does this make sense? Good. It's kind of like, hey, this makes sense, actually. Let's get rid of machine learning. We know we're way into machine learning phase here. So, how do we build R? So we have n samples. I sub I, comma, S sub I, or I, and there are n of these. I equals 1 to n samples. What we're going to do is sequentially learn the regressors. So the first thing we're going to do is each regressor is going to be learned explicitly, minimizing the sum of the alignment errors. So this is going to be, I'm going to write down another equation. And it's kind of a magic equation, but just write down. N. Oops. Minus. Oops. R. R. So now this is where our grad student stuff comes in, right? So we have thousands of images where we have the image itself and actual location of the points that we want. We actually have the grad students go through them. So this is basically a mathematical way of saying, well, we want to find R such that for all of those shapes, all 2,000 shapes or 5,000 shapes or images, we want to find the R that moves our current shape as close as possible to the main shape. All right, so that makes actually some sense. I mean, this is just a mathematical way of doing it. And the way they're comparing shapes is they're just taking this great big vector and then subtracting it from the shape that comes out of our magical equation here. So we just subtract those two. So we subtract the current shape from the target shape. And then these bars here just mean the length of the vector that's resulting in that. So you do a basic dot product of the result of that. And that's just the sum of the squares of all the differences. So the smaller the difference, the closer this thing is to the actual shape that we're looking for, the smaller this thing is going to be. And what we're looking for is something that produces a delta that we add to the previous shape that we've discovered that works. That makes this as small as possible. And this is why we're doing it in a what's called a boosted fashion, where you solve once and then you do it again. Because you can imagine that this R can't figure it out for all shapes, right? We're doing this for every single image that we've gotten through here. So we're trying to find an R that basically gets you closer. It moves you somehow closer to whatever you're looking for, with the knowledge that we don't have to get perfect. We just want to find the thing that gets us the best. And then we'll do it again. And we'll do it again, with the hope that each time we do it again, it gets closer and closer and closer. All right. So how do we do this? Well, it turns out that each R is composed of a whole bunch of little teeny regressors. We'll explain there R2 all the way up to R. And there are 10 of these R's. There are 5,000 of these guys. So 5,000 of these little R's that are basically doing the same thing. But these guys are called weak regressors. They aren't that smart. They're very fast to execute. You can execute them all very rapidly. And what we're hoping is that if we do enough of these things, that they can basically figure things out for us. So below we describe how to learn each weak regressor. So hold on. All right. So each regressor is actually built of what's referred to as a fern. There are 5 leaves in our fern. So each one of these guys is a little fern. It's composed of 5 leaves. A fern is a composition of F features and thresholds that divide the feature space and all training samples into 2 F bins. All right, so now we're going to stop and talk about decision trees really quickly. And I've talked about decision trees a couple of times in the chalk talks, but I'm going to do it again. Say we have a list of somebody on the life size is not muted. There is a button on life size actually that is a mute button. And you can actually do it. So I'm going to actually turn you down a little bit. If you want to ask a question, wave your hands. I'll be able to see you. All right. What a decision tree is. And that's who we're at a decision tree is. Let's totally get away from image processing right now. What if I wanted to predict the price of a car given the knowledge of the car's horsepower and the size of, I don't know, the length of the car. So maybe we know we have a big list of cars where we have horsepower and length and price. And we have horsepower 150 and the length of the car is, I don't know, 85 centimeters. And the next one is 220 horsepower and 100 centimeters. And the price is $10,000 and $30,000 and all sorts of stuff. And if you plotted this out, where here is horsepower and length, and started plotting points on here and attaching values to it, and I'll just write down thousands of dollars next to this. So this is 15 and 20 points over here. We got horsepower jumping all over the place and length jumping all over the place. And the price is 16 and 23 and 4, 5. Well, what you want to do with a regressor is use the input data, the length and the horsepower, which we can actually measure. And we want to build up a model of if I see a car that I haven't seen before, I could have a good guess of this data. But the data is very scattered. It's all over the place. So how do you do this? Well, a regression tree or a decision tree. The regression tree actually returns a floating point value like the price. A decision tree tells you either it is something or it isn't something. But they're very related to each other. A decision tree is basically going to take a look at this, and you're going to say, at one point, I'm going to choose one of the parameters that I have as an input, and I'm going to choose it randomly. And I'm going to say, if length is greater than some value, say, I don't know, 70, then that is a good divider of my data. So if length is greater than 70, which might be here, it divides the data into stuff that's approximately $10,000 to $20,000, and then stuff that isn't, stuff that's very expensive or something like this. This may not be the best decision. We may, as we're building this, we may decide that, hey, it actually on the first level, it might be better to look at horsepower, or actually, this is length. Length, let's do this. Right there. But after that, we might say, this data could actually be clustered even better. It looks like if I split this right here, I'd have a chunk where I have expensive cars, and then I have this guy over here, which is a 10. And if I split this again, maybe I could split what I've got over here this way. And now I have some chunks over here, and all of a sudden, I'm breaking this data. And remember, I've drawn maybe 8 dots here, but typically we've got thousands of dots. This decision tree is going to build up ways of dividing the data so that the resulting chunks all have similar values. And how it goes about doing this is very complicated. Well, it's not very complicated, but it's very time-consuming, where it's going through and looking at, it's choosing a random parameter of the data that we have, and it's choosing a random value to compare it against. It's basically saying, if I divide it here, do I get a better division than if I divided it here? Or if I divided it here, which one is the best way to divide this that kind of teases the data apart? And we literally go over this. We can continually update our division stuff to make this dividing happen. But at the end of it, what we have is a tree, and this is why things go so fast, that if you compare the length to 70 here, compare the horsepower to 200 here, maybe this is length over here to 30, and so on. At the end of it, the result that you get at the bottom is a good estimation of the price of the car if you follow the tree down to that location. I've really gone over that really rapidly, but this is what what this regression stuff does. It basically teases the data apart so that you find clusters in your data that all produce about the same result. And because this can be a very complicated cloud of data, remember we have just 2 parameters here. Here we have 68 times 2. We have all these different shapes that we need to figure out. Or take that back. We have all these pixels in here that we need to figure out. So if we took a car data and stuck it through here, we eventually could come up with a good result of the dollar sign on this. What we want is to build a regressor that, given an input image, comes up with a good delta to our shape. So instead of a price here, we're going to produce a shape change. And instead of length and horsepower, we're going to use pixel differences. Random pixel differences. So A fern is a composition of F features and thresholds that divide the feature space. Remember? So features are the features in the image, and thresholds, whether or not the difference here is bigger than something or smaller than something. And so we have 5 features, and we have how many bins at the end of it? Well, you've got a binary tree that's 5 things deep. So you have 2 to the F bins of what these features and decisions could be. So if this pair of pixels produces a thing that's bigger, well, you're going to have 5 features. So you're going to actually have 5 pairs of pixels that we're randomly going to choose in here. So 4, here's 1 more, here's 5. And each one of these guys can produce a difference that is either bigger than a threshold or smaller than a threshold. So you could treat that as a binary value. We have 5 different samples, 5 different thresholds. There are 2 to the 5th different possibilities given this pixel, these pixels in the image. So this is actually kind of cool. You could use this all over the image, right? You could take this little shape and you can move it all over the image, and you can build up a little histogram. You could put, you know, if I run that thing over here, I get this result. If I run that thing over here, I get this result. And I can bin the results. So a fern is a composition of 5 features and thresholds that divide the feature space into all training samples into 2 to the F bins. Each bin is, B is associated with the regression output, delta S. So each one of these guys is a delta S associated with it. And the whole goal of this is to say, I can use it here. We want to find the delta S sub B equals arg min. This is, again, sort of a little weird, but I is equal to all right. Now what's this? These are the images that fall into one of those bins. In bin B. So we have, of our 2,000 training sets, we may have some of them that fall into that guy. Now, because we know the true shape and we know our current shape, we can actually calculate the delta S. And the delta S is actually pretty easy. You know, this seems complicated, but it isn't. It's SB is equal to the sum of all these guys, I equals omega B, the number of things, SI hat minus SI divided by the number of samples. So this is basically saying, oh, okay, if I have a whole bunch of faces that, because of doing this feature comparison, all ended up in the same bin, and think about what that means. That means that this pixel was lighter than that pixel. This pixel was darker than that pixel. This pixel, you have basically the same pattern showing up in all of these images. Then that might mean that the change that I make to the shape should be about the same for this thing. So I can calculate that. I can take all the images that fell into that bin, take what has to change to this shape to make it faster, and basically we're taking the true shape and the current shape and subtracting it, and producing an average change for all those guys that have basically that same kind of pattern of pixels. Which is really cool, right? So all of a sudden, training each one of these little doodads here isn't all that hard. What's the difference between each one of these little doodads? Different pixels, just a different set of pixels. Now, how do you choose the pixels? That's a whole different thing. There's a whole another crazy thing that you have to do, and I'm actually thinking, because we only have 10 more minutes, of skipping that part. And if you are interested in that, I'll refer you to the paper. But the cool thing about this is, this is the thing that boggles my mind. So we have a set of training images with different faces. And this face might be smiling, and somebody is waving over here. And this face might be frowning, and over on the other side of the image, and this face might be, profile face. All right. So what we're going to do is look for pixels in here that all sort of, we're going to choose random pixels initially that all give us delta shapes that minimize this thing for this arc. So we're going to take all these weak regressors and apply it over and over and over again to come up with a change in shape that we think should work for this set of images. And in that first iteration of the main regressor, it just so happens that the way the pixel choosing works is that you get pixels that are widely separated from each other, looking for these great big pixel things, which is basically the machine learning casting about trying to find a face in the image. It's got these great big things saying, I happen to know that when you've got a face in the image, one side is going to be typically brighter than the other side. Or what I'll do is I'll cluster a whole bunch of these images where the lighting is coming from the right, and I happen to notice that I've got a lot of images where one side is brighter than the other side. And I'm having to look at a fairly large view of that. Then once I've done that, I get my shape a little closer to wherever the image is in that, the face is in that image. And I do it again. But the next time I do it, the pixels are a little closer to where I'm looking. They might be spread out, but they're not nearly as far apart. They're actually looking at more detail. And they're saying, oh, I found a face. So I'm going to start looking at the pixels that are closer to that to be more discriminative of what's going on in the face. And then each time the pixels sort of naturally, and this isn't done by coding it, it's just the way it happens. Because think about it, as you get the shape closer and closer to the face in the image, which is happening as this thing chugs along, you're never going to want to move the whole shape. You're not going to make a change to the shape that moves it away from the face. You're only going to start tweaking the face in a small amount. And so pixels that are close to what you're doing to the shape actually describe what needs to happen. All right? So, hopefully in order to make this thing go fast, so I've kind of skimmed over a lot of stuff. Think about what we've got. We've got something that runs really fast. There are 10 of these things. There are 5,000 of these things. Each one of these things just whips through all the images and bins them all. So it runs quick. And all it's doing is looking at differences in pixels. And at the end of this, it modifies the shape so that it fits the face. And if you look at the movies that go along with face alignment by Explicit Shape Regression, it's solid. It's really nice. So the synthetic guys, the paper, we're going to shift gears back to this, knowing that we have this tool that we can train, said, oh, that's awesome, but I don't want to. I want fanciness. So he said, no, we don't want that. We have our fancy blend shape. And the fancy blend shape has a whole bunch of parameters. So instead of representing our shape as 2D locations in the image, we're actually going to represent our shape as we're going to have the same thing. The face model, state S. This used to be this, and just a list of pixels in the image. Now it becomes this. A, R, T. Describes a face expression A. So A And I chose these values wrong, but remember our blend shape, it's B0 plus sum of A, I, B, I minus B0. That's the A's. So A is a big list of expression parameters. So these are blend shape weights. And it goes to M. Is it M? I think so. R is rotation. And that is a X, Y, and Z rotation vector. T is translation. And that is an X, T, Y, T, Z, T translation vector. R, R, R. So these are angles, these are translations. That's the thing that's describing our state, not these pixels, but this thing. But quite frankly, it doesn't matter. As long as the regression tree works the same way, whether we're trying to figure out changes to the pixel location on the image or changes to our face state, works the same. All right? And the pose of the camera, we're all good with that. All right, our framework predicts the change in the face model state S between a preceding frame and a current frame, which is a bit of a change here. With the previous paper, they were just trying to find a face in the image. But these guys said, hey, we can do an optimization. We happen to know that our actor is going to be front and center inside this image. So rather than trying to figure out all the parameters without knowledge, what we're going to do is assume that this is part of a sequences of images, right? And so we have the actor in this shape with a certain state that we've already calculated because we're done with that image. What we're actually looking for is the change, let's use a different symbol, delta S, that takes where we were and moves it to this place. So instead of looking at just this image as if it popped up, I'm actually saying, you know, the actor has changed. All I want to know is the subtle changes that we need to make to this to get it to the next frame in the sequence. Clever, this was very clever because it makes things a little bit easier and faster. So our framework predicts the change in face model state between the preceding frame and the current frame when presented with an image I that corresponds to the current frame. This enables what's called online tracking, which means that online just means that it's always updating itself. All right. The functionality is implemented by augmenting the input training pairs, which is this and this. So this is trained with I and let's see, N, comma, S, N, which is the shape of the face in that image, plus S, M, which is the shape that was discovered by the previous thing. Notice that this doesn't have a hat. This isn't the true shape. This is whatever we found in the previous frame. So these are training. And how many training things? Lots. We have lots of images here because we can render these guys. So we're actually going to be rendering a ton of training images. And so we'll have a whole bunch of images of a ton of this model that we've created, rendered from a whole different point, a bunch of positions and expressions. And at each point, because we're rendering it, we know the exact values that we're looking for. This is what happens if you run the current algorithm on the previous frame. So it's not exactly what we got, but it's what this thing told us we got given the previous frame. So that can be used to train this. And notice that there are lots of different previous frames. If I'm acting, the frame that came before doesn't always have to be this frame. It could be a whole tree of frames that got me to this location. So there's a certain number of frames that could have preceded this frame. So not only are we rendering sequences of images, but the sequences are varied. We have different performances, and one training frame might be followed by different previous frames, which makes sense. All right. 1 minute. All right. Well, actually, we're going to go through this pretty quick, but what the paper finally says is the algorithm in face alignment works. It works actually really well if you train it with this data, knowing those training shapes, and instead of trying to find 2D pixels, it can actually find the shape and expression of the face. But when you say blots, that gets really scary. This is a yikes moment. And the paper's actual title is Synthetic Prior Design for Real-Time Face Tracking. So the last part of the paper is saying, all right, we can render a ton of images. But when you have a ton of images, training this system takes literally forever. It takes way too long because there's so many pixels and so many things to do. So is there a way of designing this system so that you don't have to train it with as many images? The answer to that is yes. So optimizations. First, only number one with a bullet, use one blend shape. Wait, at a time. I guess I should say at a time. And this blew me away when I first thought about it. If I've got this thing and I can render it in any expression, and I'm building this training set, don't I want an image where an eyebrow is up and I'm smiling, compared to an eyebrow is down and I'm frowning? Don't I have to have all the combinations of that? And they say, actually, no. You don't have to do that. When we're actually rendering our images, all you need to do is vary one of these blend shape values up. So we've set one of these guys to 1, and all the rest go to 0, and we have this blend shape of basically the fax pose, right? So we're only using fax poses when we optimize this. So instead of rendering all the different possibilities of A going from, 0 to 1, maybe you do every 10th frame. No, you don't do that. You just go, A goes from 0 to 1. And when A is 1, all these guys else are 0. All we're doing is using one blend shape at a time. 2, camera motion is defined, is modeled. And so you don't have to move the camera in every possible position. We know that this camera rig only bounces like this. So they have reduced the number of images that are the combinations of cameras that you need to have. And then finally, intensity. The lighting changes. How do you need to deal with that? Well, it turns out that what you need to do is you have your little, let's try this as expressions, views, and intensity, or cameras. So what we're going to do is take our expressions, and we have 80 different expressions here, and we have a certain number of views here, let's say 40 different views. And we're going to render this combination exactly. We're going to have a whole bunch of views and expressions that we're going to render each time when we're generating training data. But it turns out for intensity, all you need to do is render the base view with the base expression a bunch of times. So all of a sudden, instead of having this entire box filled with data, like that, all you need is this plane of data and one row of data going this way. So you've taken this B times E times I number of images that you've done, which could be enormous, and really shrunk it down so it's just V times E plus I, which is awesome. And then where this trains in a very, very long time, this actually trains pretty damn quickly. And you really worry about this, because setting this up, first of all, you have to build the blend shape rig and everything, but then sitting there and pressing train, and it takes 2 weeks to train it, which is totally conceivable. This will take only on the order of, less than an hour, I guess. But once you have this, you get the results that they showed in the YouTube video. You have this amazing thing where, based on pixel differences in the image, that can figure out not only the expression of the thing, but the pose of the face, and like I said, the intensity that they're a little waffling on. They're not gonna say that they can actually compute the lighting model of the face at this point, but that's obviously for future research. Boy, did I go through that fast. The reason I went through it really fast is because, one, I don't understand it all, and two, there won't be a Chalk Talk next week or the week after that. We're going on a Thanksgiving hiatus. So I didn't want to wait this all in. It doesn't make any sense whatsoever. It's actually kind of, I don't know if it did. The results are staggering. But then it also takes a lot of preparation. The cool thing is that it is perfectly possible in this day and age to train a machine learning thing based on rendered images that works for real life. All right? Thanks, guys. Thanks for putting up with that. And I'm going to say goodbye, because I know that we're over. Bye, y'all.